wants to introduce Sergey, but surprisingly, he's not here. Let me double check. Okay, in this case, let me start. First of all, hello everyone. Nice to see you again. Today we have 6 talks on the colloquium series this year. And as usual, first of all, I would like to acknowledge the traditional owners of the Australian lands and pay my respect to the elders past and present. Today, I'm happy to present Sergey Frolov, who is a professor at the University of Pittsburgh. Sergey is one of the leaders in low-dimensional systems, including topological superconductivity and Majorana fermions. Sergey has received his PhD degree from the University of Illinois at Urbana-Champaign in 2005. And after 2 postdoctoral appointments in the University of British of Columbia and Delft University of Technology, he has become a faculty at the University of Pittsburgh. He has got a number of prizes and fellowships, including the ones from the National Academy of Science and the Alfred Sloan Foundations, as well as NSF Carrier Award. Okay, so Sergey, please feel to start, and we will enjoy the talk. So as usual,
thank you.
Encourage questions, interruptions.
Yeah, interruptions are fine. You know, I'm here for you. We're not overwhelmingly too many people, so I think it's fine. I do have several parts of the talk that are connected to get to, but it doesn't matter if I don't. Whatever you find interesting, and I am grateful for the invitation. You know, we're trying to cut down on travel, although Australia is one place that I would not want to cut out and eventually visit, but I have never been so far. Well, my first slide has been this slide for the last 6 months. I am from Ukraine, and you probably know that terrible war is happening in Ukraine, and it keeps us gripped, all the people related to Ukraine, constantly. I am not from Kharkiv. I'm from Zaporizhia, you know, the nuclear power plant city. But this is the pictures that from the beginning of the war that we as physicists can perhaps relate to stronger, because this is a Kharkiv Institute of Physics and Technology, a place where yeah, Shubnikov worked, and yeah, and it's been damaged in the first days of the war. And Kharkiv is a place where a lot of physics is done. So for instance, I work with nanowires lately a lot, and I've been inspired a long time ago by this paper on lead telluride nanowires, where they were grown in Kharkiv in a different institute. Yeah, I'm actually trying now to work with these people, Valentin Volobuyev, to grow some of these wires, and we have some work on this material. Right, but okay, I work at the University of Pittsburgh, and we have a pretty large group by now, so about 10 PhD students and some postdocs, and we are, you know, funded by United States government mostly. So I'm grateful to my group, and I will be showing you results from some of them. And I have a separate slide to acknowledge all the crystal growers that we work with, because we do make nanoscale devices in Pittsburgh, but we cannot grow these wires. This is a special art and skill, and it takes an entirely new expertise and group. So we work with teams from places like Eindhoven and UCSB, and increasingly from Grenoble and Toulouse, and hopefully we'll start working with these people from Poland and Ukraine and others for the wires. Okay, so I see the audience is very high level. I think so, but it is a colloquium, so I'm going to start from very far. You know, superconductivity. So we work with superconductors, and the remarkable thing about them is that they lose their resistance, and this was discovered over 100 years ago by Camerlingonis, measuring mercury. And this is a slide that explains the coupling mechanism in superconductors. And if you already know it, that it's a coupling of two electrons, you'll be amused to look at this picture, because this is a picture when I was a grad student. Leon Cooper actually visited his old stomping ground, Urbana-Champaign, where I was a PhD student, and I printed this picture for him, and he signed it, and he wrote, "Nice work." So I don't know what he meant. His work was nice, discovering Cooper pairing, or my job drawing this diagram, which actually has a mistake. So I guess especially the theoretical physicists among us can point this mistake to me proudly, but I already know the mistake. But so you can keep it to yourself. Anyways, it's a Cooper pairing, coherent correlations between electrons in a condensate. But what I am interested in is not the superconductivity and its mechanisms itself, but what interesting thing you can do in a proximity regime where superconductivity kind of leaks into a non-superconducting material. So the easiest thing to think about it is in real space, correlations between spins and electrons persist when they sort of fly into the non-superconducting material from the superconducting material. This is a very crude and even inaccurate picture, but it gives you a lot of the right intuition. And then another way to think about it is to connect the superconducting and non-superconducting conductors. Well, one has Cooper pairs, so pairs of electrons. The other one has single electrons. Theorists came up with a process. Andreev came up with a process of Andreev reflection, which converts one charge into two. So what happens is an electron comes to the boundary and scatters off, but it scatters into a state below the Fermi level, so into a hole. And as a result, a charge of 2e is transferred forward, and charge of sort of minus e is incident, and plus e is reflected, so there is charge conservation. So these are two views of the proximity effect. And I'm interested in the proximity-induced superconductivity because it unshackles us from some of the restrictions that bulk superconductors put on us. For instance, it's much easier to put something like magnetism into the non-superconducting material than it is to stick it into the superconductor. And magnetism is an interesting control knob to kind of torture superconductivity, because in all, or I should say in most known superconductors, this Cooper pairing involves spin singlets. We're looking for some interesting superconductivity where we can twist the spins out of this singlet order. So maybe create a triplet superconductor or some kind of spatially inhomogeneous state like full de Ferrell-Larkin-Ovchinnikov state, or this topological superconductivity, which involves Majorana fermions. It's just easier to do it not in the bulk, but in the proximity region nearby. You have less restrictions. Yeah, so this is another view of Andreev reflection here. So one example of a state that could be realized in the proximity regime, so in this unshackled superconductivity, is this Majorana state. And this has been my research topic for the past 10 years plus, probably 12 years. And my main topic. I also worked on other things like spin qubits, etc., just mesoscopic effects, but this is sort of the uniting theme of all my research. And it's one of those things that it's an interesting piece of condensed matter physics, but it also has this connection to the foundations of quantum mechanics and to particle physics, because The equations it goes back to are by one of the classics, Non-Majorana and even Eddington before him. So 1930s, they were solving the Dirac equation and they found special solutions where solutions produce wave functions or operators in the second quantization that are their own complex conjugates. So it's like they're real operators. Complex conjugate is the same as the operator. And in the language of particles, it means that particle is equal to its own antiparticle. That's fascinating. And I have all these analogies on the screen that I've been showing for a while. This tennis ball and balanced in the water, perfectly half submerged. So it's one with its reflection. So like antiparticle and particle are one thing. Right, so where you might look for them in a condensed matter system, if you want a particle that's an antiparticle, it's like you want something that is an electron and a hole at the same time. So for instance, if you have an equal superposition of an electron and a hole, then if you conjugate that, it becomes an equal superposition of the hole and an electron, so it becomes itself. And equal superpositions of electrons and holes is what you find in superconductors. That's what the Cooper pairs are made of, and well, of superpositions of electrons and holes. And in this case, it's not electrons and holes like particles from conduction and valence bands of a semiconductor, not separated by a huge band gap. It's these electrons and holes in the Andreev reflection sense, so slightly above the Fermi level in a metal and slightly below the Fermi level in a metal. So here I showed in a Dirac band structure where electrons and holes are completely connected. So that's a closer analogy, that at the symmetry point in such a Dirac spectrum, you will have an equal superposition of an electron and a hole at the degeneracy point. And in superconductors, we can have something similar. We can, in fact, have a Dirac spectrum in a topological superconductor, and then at the boundary, you will have these superpositions. Right, so they exist actually in any superconductor if you pick the energy right, but they're not stable. So any scattering will destroy these states. So one objective is to stabilize them so they can become a resource for more advanced experiments like manipulation, fusion of these particles, investigation of individual particles. And the other motivation is that they're so much more than just equal superposition of electrons and holes, right? They're predicted to be non-Abelian. So actually not fermions. They're colloquially called Majorana fermions, but the correct way is to actually not call them fermions, call them modes or states, etc. Because they're not fermions and they're not bosons. So they're something else. And you can see that if you try to move them around. And they obey these rules that you can see on the screen, first derived by Moore and Reed in 91, which if you apply these rules, you move them around, you will see that it's non-Abelian because, for instance, well, you know, out of two real numbers, you can create a complex number. And a complex number in the language of Dirac equation particles, that's just like an electron or a hole. Electron or positron. So I can create this superposition out of two Majoranas, which gives me, let's say, an electron. So I denote it by C dagger, because electrons are particles, so I create them C dagger. And then if I move the two around, change their positions, and I apply these rules that are on the screen, gamma goes to gamma 1 goes to gamma 2, but gamma 2 goes to minus gamma 1. And if I put them together again, out of C dagger, I created a C. So out of particle, I created an antiparticle, a hole. But then these are complex fermions, so they are not their own antiparticles. So this led to disappearance of a particle from the system, it seems. Well, this paradox has a solution. the particle actually goes someplace else in the system, so it all checks out. But this is kind of a remarkable property, and there are no such particles in high energy physics or any field like that. So that's pretty interesting, I would say. And some people took it very far, right? You're probably aware, many of you know, that there is an entire quantum computing paradigm called topological quantum computing based essentially on these operations, moving around non-Abelian particles, which could be Majoranas. And in the knots, in the timeline knots of these particles, in the braids, you can store information, or you can perform logic operations with this information by how the particles are created and annihilated by moving around Majoranas. So that's a pretty far-reaching idea, I would say, and we don't even have very strong evidence that it might work or that it has any advantages for quantum computing. But if we could just do, sort of one braiding operation, I think it's indisputable that that would have, interest from the fundamental point of view, sort of cool experiment. Right? And that's as far as I'm taking this. I would love to do that experiment, and we are still very far from it, but maybe I'm still not completely gray, so maybe I can still do it. So what have we been doing so far is looking for evidence that these Majoranas can even be created. And the way we've been trying to do it is in semiconductor nanowires that I already advertised, that there are these great objects that are sort of one-dimensional crystals of semiconductor, like indium antimonide or indium arsenide. And we need superconductivity for superpositions of electrons and holes, and that we get by proximity, which I also advertised, that it's much more flexible to induce superconductivity by proximity. So in a superconductor, we can induce superconductivity from a metal like niobium, aluminum, tin, lead, etc., a simple metal, which is a reservoir of spin singlet Cooper pairs. And in the nanowire, we need also a couple of special things. We need magnetic field to lift fermion degeneracy. Otherwise, we have two Majoranas on each end. And we need spin orbit interaction that makes peace between magnetic field and superconductivity. That's also kind of easy to explain, because superconductivity, as I said, it's like singlet pairing of electrons, and we also need field, so that likes to twist spins into a triplet configuration, and that actually kills superconductivity, destroys it. So in the presence of spin orbit that mixes singlets and triplets, there is a way to preserve superconductivity and make it survive into this state where Majoranas emerge. So I purposefully removed from my talk the actual detailed description of how theoretically Majoranas would appear in these nanowires. I can come back to it if you have questions, but I removed it because I wanted to get to more stuff that's methodological and the consequences of this for our field, perhaps, because that's what I've been mostly preoccupied with the last, 2 years. Well, since the COVID hit, we've been working on these issues. So for the purposes of this kind of talk, all I need to tell you is that to look for Majoranas, we do this relatively simple experiment where we define a region in the wire where Majoranas may appear. So basically by covering it with a superconductor, and they are supposed to appear at the ends of this region. So I denote them with stars, and to probe them, we do tunneling measurements. Tunneling, like make a tunnel junction and detect current. If you're more familiar with STM, it's like having an STM tip parked inside the wire, because this left end of the wire, we use it as a tunnel probe on the right end of the wire. So we hook it up to this electrical circuit where electrons can flow through the wire, hop over this tunnel barrier. And if there is a state there, we don't know if it's Majorana or not, but if there is an energy level for electrons to hop onto, we get a little bit more current due to kind of a resonant enhancement of current. And then it's drained into the superconductor. So data look like this. Yeah.
Could you remind how thick these nanowires are?
100 nanometers.
Okay, thank you.
But it's a semiconductor, so you can think of electron occupying the entire wire, like a wave.
Okay,
it's like a waveguide for these electrons, with quite a bit of scattering also, but more, pretty close to a waveguide. Right, so we get these kind of tunneling characteristics, and the horizontal axis here is source drain bias. So it's basically voltage on this battery. And what is measured is conductance. Well, it's dVdI, so it's a derivative of this current with respect to the bias voltage. And the traces look like this. So they have two peaks at finite bias, and those peaks are well known, like around minus 250 microvolts and plus 250 microvolts. They're well known from superconducting tunneling measurements because they are the induced superconducting gap in the nanowire. And inside the gap, current is suppressed. It's smaller than outside the gap. So this is a small gap around the Fermi level that's due to superconductivity. It's on the sort of millivolt, microvolt scale, not the EV scale that is a semiconductor gap. Right? That's much bigger. So we are fully in the conduction band here of this indium antimonide semiconductor. And for Majoranas, we need magnetic field. So as we apply magnetic field, these traces are all different fields. They're just offset for clarity. In addition to these two large peaks on the ends, in the middle of the gap, we start to see an additional little feature, which is called zero bias peak in conductance. So like there's a little bit of extra current flowing at zero bias. Well, a little bit of extra conductance at zero bias. So suggesting there is a level, energy level, extra state at zero bias, which this current flows through. Because it appears exactly at zero bias and at finite field, this could be due to these Majorana fermions, given that also all the other conditions like the right nanowire, the superconductor are all there. These are the conditions predicted for these Majoranas to appear. And another type of plot here is very similar experiment, same materials, indium antimonide, niobium dinitride superconductor, just a different representation. And well, it's also, this was old data from Delft when I was a postdoc, when we first started doing this. And this is from my own lab in Pittsburgh, but it's also in color. So I just want to introduce this color scheme as conductance, and red is high conductance and deep blue is low conductance. So here again, around zero, you have suppressed conductance. And then you have these two peaks at finite bias, in this case, larger than here. So it's a larger gap around, I don't know, 300 maybe. And then at the magnetic field, in this case, 1 Tesla, here it's about 100 millitesla. But again, this stripe of high conductance appears at finite field, and it's kind of stuck to zero bias. So this is also important that it doesn't move in energy. So the bias at which a state appears is like the energy of the state in spectroscopy. Yeah.
Could I interrupt you again?
Yeah, sure.
If one takes just conventional superconductor, am I right that you would expect just zero signal inside the gap because it is a true gap? But here it appears that the signal is suppressed, but it looks like linear or quadratic.
Yes, it's not zero. Yeah, so I would say also in a well, say in a simple classical superconductor, there should be no conductance, no states inside the gap. There's many reasons why there would be states inside the gap and why there would be a background. So in these experiments, yes, it's a suppression, but it's not a complete gap. It's not a complete suppression of current. And so we call it soft gap.
Yeah.
This kind of soft gap would certainly have consequences if we wanted to make, for instance, a qubit out of these Majoranas, because it comes from some other states that are throughout this energy window, and unwanted states inside the qubit are bad. They expect to have a lot of decoherence from these states. For spectroscopic reasons, as long as you see peaks that are prominent, you can still study them, whether or not your background is completely zero or not. You may be a little bit limited if there's too much background. And also, a lot of effort has been put into completely suppressing this background, but for the rest, the data look the same. And I will probably show you some data with less background as the talk goes forward.
Thank you. I have another question. So it looks like if the magnetic field is too high, this signal disappears. But as I recall,
eventually
take the model by this one-dimensional nanowire with parallel magnetic field and proximity effect. I don't recall that anything could happen if magnetic field is too large. It looks like the larger magnetic field is, the better. The larger is the better.
Right. So depends on whether the model includes sort of the eventual destruction of superconductivity in the metal itself, right? So we have this host, it's kind of a reservoir of Cooper pairs that gives Cooper pairs. And at high enough field, that gets suppressed. So that's one limitation of this, if the superconductivity is suppressed in a bulk superconductor, it cannot be induced in the semiconductor. So that's one limitation. And there could be also other problems like orbital effects where you fit so many orbits inside the diameter of the wire that it dephases Cooper pairs. So there's several different mechanisms why eventually it dies out.
Okay.
So, but what's good is we have a large window here to work with. The reason also why we choose indium antimonide is it has an enormous G factor, around 50 versus 2 for free electrons, right? So for 1 Tesla, we get something like 1 millivolt or even 1.5 millivolt milli-electron volt of Zeeman splitting, of Zeeman energy. So this graph is a convenient one to show this. The span of bias here is about 1.5 millivolts. So over 1 Tesla, let's say if I go from 1 to 2, I get the Zeeman energy that crisscrosses the entire, that fits in this entire plot. So it also goes to show that if I had an electron there belonging to indium antimonide and it would just disperse in energy due to Zeeman effect, it would move from the bottom of this plot all the way to the top. And in contrast, this state that we're studying is kind of stuck in the middle. It does not move, and that's special. At least we thought it was special when we started these experiments 10 years ago. Shall I move on, or?
I have another quick question. If you look at the left plot and on the top of it, for me it looks like if the magnetic field is enough large, the peak splits in two.
So
what happens?
It may be splitting, or there may be 2 peaks that sort of emerge from when this one dies out. It's hard to tell. You can also see here a little splitting, right, in color.
But it is not what expected from how Majorana behaves?
No, it could be also a Majorana behavior. I will show you in the next slides. If the wire is finite length, then Majoranas on the left and on the right, their wave functions overlap, and then by exchange they acquire finite energy, so they split from zero. It's like if the wire is infinite, the theory predicts that these peaks are exactly at zero, and then if the wire is finite length, then you can think of it as a molecule, and you get exchange splitting, sort of HOMO and LUMO effect, but with Majoranas.
Oh, thank you.
So all this, can be explained with Majoranas, at least from the data that is on the screen at this moment, right? We study it further and further, we might find some contradictions. And that's what I want to emphasize here in this talk. So we found these peaks, we reported them, they were well accepted. People were pretty sure we found Majoranas. We were quite sure. I mean, we did study various failure modes of this theory, and the paper is kind of written carefully. It's called Signatures of Majorana rather than direct demonstration or evidence or discovery or whatever. Anyways, we were still pretty sure. And because what else could give such long, narrow zero bias peaks over that appear at finite field and behave as you expect with so many parameters, require superconductivity and spin-orbit interaction, which we also verified by rotating the field. What else could it be? Well, it could be something else. All of these things could be explained by something else. And that's what we learned in the, between 2012 and 2022. At some point, various people learned it, some people sooner, some people later, and some people are still sort of not accepting this as the truth. But the possibilities are illustrated in this plot, and basically what you want, the regime you're really after, is these this long wire, and Majoranas are wave functions that have finite extent, but that they don't overlap. It is like taking one electron and splitting it in two, because remember I told you that the electron is gamma 1 plus gamma 2, gamma 1 plus I gamma 2. So if gamma 1 is on the left, gamma 2 is on the right, and they don't overlap. That's really what we want for braiding, for, well, in reality, due to disorder, finite system size, we could be in this middle situation of partially separated, but still separated wave functions. So kind of an electron that's kind of split, but not fully split. We're kind of pulled apart. And that's called quasi-Majorana. That's also interesting. It also requires spin orbit and superconductivity and Zeeman splitting, all the same ingredients. It's just not so pure and clean. And I would still take it if I could convincingly prove it to myself that I have it. I would still take it and be very happy. But I'm not even sure we have that, because what we also learned is that completely trivial Andreev states, so some subgap states in a superconductor, created by Andreev reflections bouncing off the walls. So sort of looped Andreev reflection, where it goes into the superconductor, scatters off, goes back, and creates a standing wave, an Andreev standing wave, which is called Andreev bounce state. Trivial, referring to being non-topological, not of Majorana origin. Trivial, on one end, not accompanied by a partner on the other end of the wire, can still give zero bias peaks. And well, this is sketched here. It's a picture actually from my Twitter account. And we were supposed to write it as a review article, and we never did. Because at some point during the pandemic, it became sort of not clear which articles the review should review, because they started falling apart one after the other, all these articles. But as a concept, it's still useful. So here, the notations are: the thick blue line is the decay of the gap in the superconductor, that eventual death of all superconducting things with magnetic field, and the x-axis is magnetic field here. So the thick blue line is our envelope where we can observe anything, and then the red lines are subgap states that move to zero bias, and this shaded region with oatmeal color is the closing and reopening of a small gap inside the wire, which is a topological quantum phase transition. And upon this transition, it leaves behind this Majorana state, and it can even breathe around zero bias, like I said. For a finite side system, it doesn't have to be stuck to zero bias. And because of particle hole symmetry, there is a kind of a symmetric breathing pattern. But what was also demonstrated experimentally is that you can have a zero bias peak created by a pair of Andreev bound states that move to zero, and then they don't want to leave. They don't cross, but they stay there. And the reason they stay there is because the gap is closing, and all these states above the gap couple to the states below the gap. So blue states couple to the red states, and they anti-cross. They push on each other, so that the red states are pushed, and they're squished from positive and negative, squished to zero. So in the final section of the closing gap, there could be this extended zero bias peak. So then this concept of coupling and anti-crossings can also be applied to multiple subgap states. So here I draw, for example, red, green, and beige are three different states that live inside the gap. They are from trivial Andreev states, these standing waves of Andreev reflections, but they coexist and they overlap, and they can also anti-cross and couple. And then the lowest, the product of all these anti-crossings, is kind of pushed to low bias, and creates this appearance of look at this red state. It's not so different from this Majorana state, different in detail, but that's just because I drew it by hand in PowerPoint. And then finally, with a lot of disorder, there's a lot of different regions, sort of localizing regions, could be called quantum dots, but people often relate that to Coulomb blockade. In this case, it could just be Coulomb blockadeless dots. So just localized regions inside the nanowire, and each gives rise to something like this, some subgap state, trivial Andreev bound state, and they just sort of overlap and they crowd the spectrum around zero bias. So these are three principal non-Majorana explanations for zero bias peaks, and this has been known for quite a while now.
Sergey, could you explain again how the Andreev bound state forms? They usually have a closed loop with a quantization, but
yeah, so the more famous Andreev state is between two superconductors, where you undergo Andreev reflection on one end and then on the other end, and you close the loop like this. So you have an electron branch, and then it scatters into the whole branch, and then back into electron, and so on. So here we have one superconductor, but we have just confinement in space because we're in a nanowire and we have tunnel barriers, etc. We have roughness. So the right model for it is that as a confined region of non-superconductor next to a superconductor. And what you do is you go out of the superconductor into the normal region, you bounce around there, and you go back. So you close the loop on itself, on the same lead.
So
then you have one loop for electron and one loop for hole.
Does it mean that order parameter is in nanowire is not uniform, but has some variations, and this bound state happens between these variations? So you could have, for example, islands of superconductivity separated by normal region, and this bound state will be bound to this normal region. Is it correct?
So I started my talk by advertising this real space view of the proximity effect, where out of the superconductor it decays sort of superconducting correlations, which is the order parameter. That's the name for it. It kind of decays out. At the long enough distance away from the interface, 1 micron into the wire, it will happen. It will decay eventually. But these nanowires are quite special. First of all, they are small. So there's only a few modes, transmission modes, transmission channels in them, like maybe 10. So it's very mesoscopic. And the second thing is they're quite ballistic. So we see, quantum point contact behavior in them quite often, Fabry-Perot interferences. So they're very clean. They are still not as clean as two-dimensional systems, but they're remarkably clean for one-dimensional systems. Probably Andreev picture is much more suitable for such a system than the decaying wave function, because each wave function that comes out of the superconductor will be very different. And if there's only 10 of them, there's no point averaging them together into some kind of decaying thing. But if you do that, there could be weird peaks and dips, etc. So we've done some of that. We have a paper, PRL, on supercurrent interferences in these wires, and there's fairly complicated patterns that this can create. And I think that's the picture you have in mind, kind of. Yeah, so there could be very strange interferences of superconductivity in these mesoscopic systems.
I see, thank you. And you have shown pictures for the one end of the nanowire.
Yes, I will talk about that.
If you make the measurements at the other ends, is
yes, we have done
identical, or they have some occasional variations or differences between them?
They have predominantly difference. Yeah.
Oh.
Not much similarity, yeah. But I will show you in a second.
And I think
Olivier, you have a question?
Yes, thank you. Can you hear me?
Yes.
Yeah, so I think it is very related with what Dmitry just asked, but it's just to make sure I understand. So you mentioned how this Andreev bound states form, because I'm not specialist, but yeah, at least I know that I understand maybe this picture where you have two kinds of superconductor and a junction, and you have this Andreev bound state inside the junction. And what you mentioned here is that you can have this bound state with one superconductor, but do we understand well that to obtain this at one end of this superconductor, you also need additional ingredient, like some disorder in the normal?
Yeah, you need confinement. You need confinement either due to just a quantum confinement, a confinement in space, or a tunnel barrier, or disorder, something that localizes a wave function near the superconductor.
But and in your picture, this disorder is related with the normal region in what
well, it could be the interface of the two, the superconductor and the semiconductor, but it could also be roughness on the surface of the wire, some kind of molecules there, contamination. It could be grains in the superconductor itself, which lead to all kinds of variations in gap size and.
Okay, I see. It's not it.
It could be all of those. Yeah.
Okay, thank you.
Okay, so what to do, right? So basically, what I'm telling you is that another explanation exists for what we thought was Majorana. And this is a very powerful explanation. It goes very, very deep. So you can keep producing tunneling transport signatures, and then I can show you Andreev states that do the same. And we already know that for a number of years. So, well, I propose something fairly simple. Other people will tell you, let's do more complicated experiments like braiding or fractional Josephson effect or some other things that you may have heard in relation to Majorana. And my critique of that is that, well, if you do more complicated experiments, but you have the same disorder and the same issues, you will be braiding trivial states, right? You will just waste your time. And who knows, maybe those signatures can also be falsified by trivial states. So my proposal is, while we improve materials and interfaces and processing, we just keep doing the same experiment, the tunneling experiment, but we cross-check it across several different signatures predicted for these zero bias peaks themselves, right? And you'll be surprised, but most papers show you maybe signature number 1 here, or a couple, like 1 and 4, maybe. Okay, and none of the papers show all 5 on my list. Not a single paper does that. And maybe 1 or 2 show 3 signatures at the same time. And however, each one of them has been reported in a different experiment from different nanowire. So you can say, oh, this has been observed in this experiment by this group, and this has been observed in a completely different experiment in a different country. Well, that's not going to work. Andreev bound states can trick you there. You can fine tune to see long zero bias peaks. I can show you that. You can fine tune to see these Majorana oscillations, these splittings of the peak, which can also be done with Andreev states. And yes, like Dmitry already asked, this has to be done on both ends of the wire, because it's one of the key features of Majorana, that it's an edge state of a new quantum phase, a topological phase. So it appears at every edge. So if there's 2 edges, it has to be double, but it does not have to be even identical, because the 2 tunnel probes are different. They're mesoscopic as well, right? So we need to disentangle the effects of the probes on the bulk. But we should see from underneath the probe something that is similar on 2 sides. So yes, we have tried that. And we did exactly this experiment. In fact, we were trying to do these experiments for the entire 10 years. Even the first devices had 2 sides. It just didn't always work. But yeah, the idea is simple. So I told you about this experiment where we put a superconductor on a nanowire. It's the same material here for the sake of cohesion of the talk. It's an indium antimonide nanowire with niobium tinitrate superconductor. But now we have 1 tunnel probe on the left, we have another tunnel probe on the right, and we want to look at, well, correlated zero bias peak. So if there is a zero bias peak on the left, there has to be one on the right, and they should sort of appear and disappear for the same regime, for the same settings for the same magnetic field, for the same gate voltage, for the same parameters of this experiment. And well, it's just not what we see, even in a fairly short wire, like 400 nanometer left to right. It's not what we see. We do have receive. We can mimic signatures of Majorana on one end. In this experiment, to counterpoint this Delft paper that has been retracted from Nature, we even made the zero bias peak here on the left side. Here it is at finite field, the zero bias peak. We made it be of the height of 2e squared over h, which is another prediction for Majorana, that the peak has to be quantized in height of 2e squared over h. It's actually a very fragile prediction for theory, but nevertheless, it's been claimed, and the claim has been retracted. Okay, so we also measure at the same time on the right side, right? So we have a 2e squared over h, undisputable Majorana signature, according to that retracted paper. On the right, we don't even have a peak. We have a dip at the same field. We have something opposite. So here is no peak. And that's just to show you that in general, the two sides are not correlated. So we have quite significant disorder. In fact, if we change one of the parameters, which is this gate underneath the wire, which is supposed to tune the chemical potential there, the density of electrons, we can find a point where zero bias peaks appear at the same field on the left and on the right. So that's the yellow, the golden point. But further investigation shows that there is nothing special about that. It's just a coincidence. It's not like this is the topological state. If you look at more data, you convince yourself of that. All right. So basically, the system is still promising. I mean, all that said, all these difficulties, just the fact that we can understand it in such detail and find all these states and investigate them one at a time, you just cannot do it in too many systems. It's thanks to the tunability of these semiconductors, the already purity, the ballistic regime in which these devices are near quasi-ballistic. This is a tall bar. This is a tall bar for these experiments to reproduce in any other system like a TI or Van der Waals flake, to create 1D systems of such quality. But it's still not enough. We still need to do better. And we have some ideas. We are tweaking the system to improve the interface, to try different, more gentle processing methods to grow the wires a little bit cleaner. And maybe, just maybe, this sort of accumulates to these small incremental changes will take us over some kind of threshold, like for instance, maybe over the threshold of just proving that there is a pair of Majorana bound states on the left and on the right. I don't know if it will take us all the way to braiding or something fancy like this, but at least this. So one thing we were trying is, for instance,
sorry to interrupt.
Yeah.
A couple of slides ago, you have shown a table of 5 expected signatures, some kind of checklist.
Yeah.
Expected. So how many of them are actually satisfied for these experiments, if you think about this as a checklist?
Well, I used to have a table per
Mhm.
paper, what's been claimed, but now that I don't trust 2/3 of the papers on the list, like I think they should be retracted for data manipulation or bias data selection, I don't show it anymore. But basically, like I said, with words, it's something like 1 or 2 signatures in each paper.
I see.
Sometimes 3, right? But never all 5, and never the 5th one. Although that's been receiving more attention lately.
I see. Maximal 3. Okay.
Yeah, because my 5th one is defined not as 0 bias peaks on 2 ends, but the first 4 signatures on 2 ends. So that's not been done.
But is it possible if, I don't know, if occasionally superconductivity is somewhere suppressed inside the wire because some region is more disorderous, that you will have 2 pairs, that if you have superconductivity field,
it is possible, yes.
We could have 2 or even more pairs of Majoranas inside the wire.
It is possible, but then my approach is start with the shortest segment.
I see.
And then try to make it bigger. And we already got stuck at the aspect ratio of like 4:1, right? If the diameter is 1, then if the segment is 4, we already stuck at that. And other groups like Microsoft show you wires that are, I don't know, 10 microns long. Well, that's just hopeless.
And am I correct, if you have Andreev bound state, you always have a pair of states? They can be easily tuned, or in series they can be, their position can be tuned and they will go similar.
This is correct. Yeah, I mean, it's the same state, but it appears at positive and negative bias. Yes.
Okay.
It has sort of an electron part and a hole part.
And if you have this zero energy feature, is it possible to split it? If
it's an Andreev bound state, it's possible to split it because it's not robustly stuck to 0. It could be stuck by some
Mhm.
anti-crossings, etc. So you can also fine-tune yourself to a regime where it doesn't want to split.
Oh, I see.
So if you're just looking around for such a feature, you will find it, and then you can call it Majorana, but you know you can't in good conscience do that because you know there is another explanation, and it's very powerful.
Okay, thank you.
Okay, I don't know how much you want me to go on. It's already an hour. Anyways, we are trying different materials, etc., and even non-epitaxial seems to work, which is promising because that opens up possibilities. So things like tin, my group now works actively on tin shells instead of niobium or aluminum. We work with indium arsenide wires, lead telluride wires, etc. So we are exploring the material space. But I did mention a couple of times this related development that some of these papers were unreliable. And I'm not going to go through them, what the problems with them are. You can read about it on the internet, on my Twitter blog, or on Zenodo. We have a bunch of analyses of these papers, or you can, don't read the retraction notices, because those are also written by the authors and they're not admitting to their mistakes. But made me think that we have actually a problem, and Majorana is a perfect illustration of it, but it's not limited to Majorana. It's this desire to, find a miracle, discover a new state of matter. Majorana is one such state. And yeah, so I wrote a couple of things last year when I was deep in it. One of them is this physics, APS physics opinion. So you think you discovered a new state of matter. Are you really sure, right? You have to be careful. That's the idea. And it's summarized by this diagram where, Majoranas are in this intermediate regime where you can find some evidence that it could be it, but you are not sure because the disorder is just a little too large and the energy scale of the state is just a little too small. And so you are kind of at the boundary of possibility. You're in this, what I call the fog of hope. You're not seeing it clearly because it's in the fog, but you're also in the fog yourself. You want it to be true. So it's kind of an interesting state in between, right? Yeah, so you can read about that. And what people do in these papers that is a big problem is essentially cherry picking, but I can explain it with, with these nanowires, for instance. So the way they grow the wires, they grow from a chip as a forest. And what we want is straight, beautiful, uniform, long, narrow wires. And this is what I highlight here in the picture. In the middle, but then if you look at the background, the dim background, you see all kinds of beasts there, the tilted ones, the non-uniform ones, the flakes, the ugly clusters, and this is all in the same wafer within microns from each other. But I'm just not going to show all this to you, and I'm going to show you that, I'm going to tell you that I can grow these perfect wires, right? So this is the problem with selecting your data. And with Majorana, you can do the same, right? You look around, you find the beautiful peak. You don't have no justification to say that this is Majorana because it doesn't check with all the other 5 criteria on my list. But nevertheless, you go ahead and write the paper, send it to Nature, Science. This is bad. And, problem could be just the journals themselves could be the problem. They want you to do this. They give you a quick reviews and they just, they essentially facilitate this. So one thing I've been doing is sending my papers not to these journals and not even to physical review, but to a new initiative called SciPost. And this is done by people from University of Amsterdam, and they are physicists, they are peers. They wrote a nice website. And what I like about it is you just give them the archive URL, which archive is, the place for everything, but except peer review. So they just do peer review for you. And what is also nice is, this is a page. You can see the referee report submitted with the names of the people. If they want, they can disclose their names or they can stay anonymous. And what I also interesting is that this is not my view as an author, this is public. So the discussion of the paper is happening in public. The peer reports are online, and you can also contribute. You can log in right now and write something, whatever you think about any of my papers that are now a lot of them on SciPost. And we are kind of slacking with replies to referees now, but I promise that we will keep it up. And another problem that can be easily solved is that people hide data. Well, we can ask them to share the data, and there is tools to enable it. So for instance, if you don't know, there is Zenodo, gives you 50 gigabytes of space storage per paper. And so if your experiment fits in 50 gigabytes, you can just upload your entire data. So for us, for instance, for these Majorana experiments, it's 1 or 2 gigabytes per paper. So we were just dumping our entire data folder, our entire PowerPoint of analysis, hundreds of PowerPoint slides of, what this data is, what that data is. So my group just does it for every paper now. And so you can get all of our data, like every single data set that's been taken in the last sort of 5 years. And we're going back in time. So with these two things, open review, submit your paper to archive, facilitate open review, don't send it to Science or Nature or even physical review because they're hiding reviews. Put the data online, we can cut down on unreliable claims dramatically if we all do this. And so this is what I've been sort of promoting as an idea. But back to the physics summary, I have to stop my talk. So I am here to admit the claims of the discovery of Majorana have been overblown and are false. Majorana has not been discovered in nanowires. I don't believe in any other system it has been discovered neither. Nanowires is still one of the best, the most tunable, the cleanest materials out there. I still think we have a pathway forward through incremental improvements in fabrication. The good news is that the technique, the method of studying these Andreev or subgap zero bias peaks has been perfected now. We see them and we see that they're not Majorana, right? So when it is Majorana, we will be able to tell. So the technique is there. The processing and fabrication of materials needs to be improved, and we should be able to get there. And so this is my talk, and there's already been some questions, but I'm happy if you want to stick around and ask more. I'm here for you.
You don't hear me, sorry. First of all, thank you for a great talk. And let's go to questions. We have raised hand from Augustine. Augustine, please just go ahead.
Hi, can you hear me?
Yeah.
Hi, Sergey. How are you?
Good to see you.
Nice talk. Yeah, it's been a while. I have two questions. One is you focus on the semiconductor nanowires. There are these other platforms consisting of the ferromagnetic chains on superconductors, and they also claim to have seen a Majorana in this extremity zero energy modes. So can you comment on that? I mean, do your five criteria also apply for those systems?
Yes, so those experiments go back to Ali Yazdani's group 2014, right? So if our first paper was 2012, 2014 is pretty early on. What people have done is a metallic surface of a superconductor and spread magnetic atoms on the surface in a kind of a chain, trying to reproduce the same Hamiltonian, but with different material ingredients and on the atomic scale, really. But there's the same ingredients: magnetism, superconductivity. There's spin orbit somewhere. They don't know where, but maybe in the superconductor. So I'm pretty sure those initial experiments early on will not satisfy the criteria. Probably wasn't Majorana. There's probably some end state also. You know, you're gonna look around and you find some chains with an end state. So there will be not identical but similar criteria. Like for instance, right, you can probe on the two ends of the chain and see if it looks the same or different. Spin orbit criterion, I don't know if that'll be satisfied, because in our case we can rotate the field and check the spin orbit anisotropy, and they cannot do that. So it won't be an identical list, but there will be a list of criteria you can check with the same STM tip, just moving around the wire. There has been very impressive work from Wiesendanger and Hamburg groups, Jens Wiebe, where they don't claim Majorana, but they have a very good understanding of their system, because what Ali Yazdani and those people early on were doing, they were sort of dumping a cluster of iron atoms and a chain would spontaneously stretch out of it. So it was an impressive technique, but you know, the questions of uniformity, and also one end had the big cluster on it, so it was not so well controlled. And now these guys, Wiesendanger and Weber, they assemble the chain one by one, and as they add one atom, they scan, and then they add another one, they scan, and it sort of makes sense at every step. So they build it from zero, from nothing to a fairly long chain. The reason they don't claim Majorana is because the chain is too short. It is pretty long. I mean, to assemble 40 atoms in a chain is a super impressive work. But it's kind of limited by the width of the terrace, as far as I understand. So the surface has terraces, and they sort of go to the limit of what the terrace allows. Maybe they have already solved some of these issues, but I would watch that group. And then the question is, of course, well, if the chain needs to be 10 times longer for Majoranas to develop in it, then maybe it's a tall order. But at least they can prove that they're in the right regime to, in principle, do it. So yeah, I think that's sort of the leading work there. They deserve a big shout out.
Thanks. My second question is, with your side-post Zenodo approach, do you see a challenge, or have you encountered a challenge in terms of your grant applications being accepted? You know, like when I write a grant application here, they always ask for the high impact papers. What's your take on that?
Honestly, I don't know yet. I've started recently doing this. I can tell you that I was getting grants declined, quite a bit of grants declined, when there was this shadow hanging over our field of, you know, sort of the trust was eroding in the results, and I thought I had good ideas and I would put them forward, but they would say, oh, but you know, this whole thing stinks. And since I started telling the truth, I got so much money, you wouldn't believe. I got millions. So I have some secret supporters out there in the funding agencies or in the referee panels, where I think people actually appreciate this. So if I extrapolate this forward, I think actually there is a lot of demand in the community that is not spoken. There is fear, fear to start doing it, like the first man starting at the disco to dance and everybody standing around the wall. But there is a lot of desire to do things in the open, to be honest, and to not worry about impact. You know, eventually we can just tell the funding agencies, this is where we publish now, so go away. You know, this is what we want, and they will fall in line.
Okay, yeah, thanks a lot.
Thank you. Do you have any other questions? Please just go ahead. Let me ask one. How long is the review process in SkyPost? Is it comparable?
Well, currently the bottleneck is us replying to the people who put the time and effort in actually reviewing our papers. I feel like it's pretty good, yeah. And the good thing is they appear instantly, right? So you can even engage with one referee while the others are still thinking, in principle. You know, we've not been doing that because we're still partially in the old mold of sort of getting all the reviews and then thinking about them and then spitting something back out. But we could just engage with them individually.
Okay, it sounds quite interesting. Any other questions? You have a last opportunity. Please just go ahead and ask. If not, let's thank the speaker again.
Thanks, everybody.